All right, so maybe I can start. I'll be talking about fluctuations in first passage percolation. And so this word fluctuations is not so precise. The question we want to answer basically is the question of how close the passage time on the one hand, but also the geodesics. How close are they to their deterministic approximations? Okay, so we'll mostly focus on the passage time, but I will mention some things about geodesics because for first passage percolation and also related models in 2D statistical physics, there's actually a close relationship between these two fluctuations, namely how close the passage time is to its deterministic approximation and how close geodesics are to straight lines. So first, if we look at the passage time, what are the deterministic approximations we're talking about? If you look at T0 and E1, this is the passage time from the origin to the vector n times 1 and then all zeros. I can approximate this on the one hand by its expectation. So I can subtract the expectation. That's a deterministic quantity that we usually use to approximate a random quantity. So we could ask how close is t to its expectation in general or on average. But we also have another choice coming from the first lecture in Basu's lecture. He talked about the limit shape, right? So we have another approximation, another possibility for an approximation, which is n times this time constant in the E1 direction. So the shape theorem or the subadditive ergodic theorem tells us that this quantity here divided by 1 over n converges to this deterministic number. And so n times that number is an approximation for this random quantity, where we can split this difference into two differences. One is the more traditional difference between a random variable and its expectation, and this is what we'll call the random fluctuations. And then this difference here, which is actually the difference between two deterministic quantities, but in this field, this quantity is often called the non-random fluctuations. So we will mostly focus on this one in these lectures, but I just want to mention a little bit about this because it's also an interesting topic of research that's not fully settled. So you can ask, what is the size of this difference here? If you remember Jack's lecture, he reminded us that if we're looking not at the random quantity, but just at this deterministic expectation, we don't need the subadditive ergodic theorem. We can just use Feketa's lemma and find that this quantity properly normalized, so if we divide by n, actually converges to a certain number, which must be actually this time constant. And if you look at Feketa's lemma, you actually find that mu of E1 is equal to the infimum over n equal to 1 of 1 over n times the expectation E0 and E1, so that this guy here is actually going to be positive or non-negative at least. And the question you could ask is then, how close is it to being 0? And again, I'm not going to talk very much about this, but the intuitive, the thing to remember is that in this model, in first passage percolation, and actually in many models that have shape, in many 2D models that have limit shapes, these non-random fluctuations turn out to be, or are expected to be of the same order as the random fluctuations. For example, if you look at random matrices or last passage percolation, first passage percolation, these two terms are actually of the same order, although this is not always proved. So what does this mean exactly? So we can define an exponent, gamma bar, which is the rate of growth of this quantity. So t here grows toward the n, so if we subtract some centering, we might expect, if we're physicists, that this difference here will grow like n to the gamma for a certain gamma. And if we want to make this rigorous, we define gamma as, for example, the limb sup as n goes to infinity of the log of this difference, which we're allowed to take the log of because this is non-negative. So we take the expectation T0 n E1 minus n E1 and divide this by log of n. So again, if this quantity grows like n to the gamma, then this difference would be equal to gamma, but we can always consider this limb sup here. And similarly, we can define gamma underline as the limb inf of the same quantity. Okay, so there are a few results about these exponents that I'm just going to state here somewhat vaguely. So one type of result, one person who worked a lot on this is Ken Alexander. And if you pull together a bunch of his papers and then you can summarize the result of his work as follows. He tells you that under reasonable conditions, so if you know that the random fluctuations are of a certain order, then you can get an upper bound for the non-random fluctuations of the same order. So he has an upper bound for non-random fluctuations. So in other words, an upper bound for gamma bar in terms of the random fluctuations. So that's 1/2 of this intuitive statement, which is expected to be true, but again, not proved, that the non-random fluctuations are of the same order as the random fluctuations. So we can upper bound the non-random fluctuations, so gamma bar, in terms of the random fluctuations. And what does this mean exactly? It means that if you know that this quantity, t minus its expectation, is concentrated on a certain exponential scale with a given exponent, then that exponent you can use as an upper bound for this exponent, okay? And then there is not exactly matching work, but a complementary lower bound due to Jack and Michael with Auffinger, where they look at bounding the non-random fluctuations below in terms of the random fluctuations under some moment assumptions. They get a lower bound for the non-random fluctuations. So this difference is not 0, it actually grows like n to some gamma underline. If you know that this difference, say the variance of this difference, is large enough. So lower bound for non-random fluctuations. So again, I'll mostly ignore this issue in these lectures, but I guess it's an important thing to mention because so far we've mostly discussed, in the previous lectures, we've mostly discussed approximating the passage time in terms of n times the time constant. But from now on, I'm mostly going to be discussing the fluctuations of the passage time in terms of t minus its expectation, okay? And if you're interested in the non-random fluctuations, you can look at these papers, but you know, the expectation is that the non-random fluctuations are matched by the random fluctuations. Any questions so far? Okay, so what about the random fluctuations? So as I said, in these lectures, we will focus on the random fluctuations. And what's the expectation in this case? Well, it's expected, although very far from proved, that T0 and E1 minus its expectation grows like, oh, I'll write this symbol here, but a big part of the problem is actually making sense of what this could mean. Grows like n to the 2 chi. So it has some polynomial growth where chi is positive and is called the transversal, fluctuation exponent. The fluctuation, it's called the fluctuation exponent. Okay? So what does this mean? And why is this expected? The first thing is that it's not very clear what exactly this could mean. One way that you could interpret this approximate equal sign. Yep. Oh yeah, okay, that's right. So that's correct. This is chi. So one way to interpret this is in terms of the variance, right? If you want to say that T minus its expectation, or a random variable minus its expectation is of order n to the chi, well, perhaps the simplest way to interpret that is to say that the variance of the quantity is of order n to the 2 chi, and that's what I meant over there. So a possible interpretation of chi would be that the variance of T and E1, so the passage time between 0 and E1, is bounded above and below by n to the 2 chi. Okay, so this is not known for first passage percolation models. As we will see, I think in Martin's lectures, for certain last passage percolation models that are integrable, it's possible to prove this strong interpretation of the approximation of the random fluctuation exponent being n to the chi. But for first passage, this is not known. So the best we can do is give certain bounds. Okay, so this is only known for certain last passage percolation models. And so this will be in lecture, then course 4. Okay, so I think this is the highlight of course 4, deriving this not just this fact, but actually identifying what chi is. Okay, any more questions? So at the beginning, I stated that when we talk about fluctuations, we're interested in the distance between the actual passage time and its deterministic approximation. So there's two possibilities here, either the expectation or n times the time constant, or the distance between geodesics and their deterministic approximation. And the reason I mentioned geodesics is, even though I'm not going to talk very much about geodesics, it's important to mention them because there's partially conjectural relation between the exponent n to the chi here and another exponent that describes the fluctuations of the geodesics around their deterministic approximation, meaning straight lines between the endpoints. And this conjectural relation extends far beyond just first passage percolation. It's supposed to be true in many 2D statistical physics models. And it goes under the name of KPZ scaling. Okay, so for a large class of 2D statistical physics models, including certainly first passage percolation, but also last passage percolation. And in this case, actually, the expectation can be proved in some cases, and also directed polymers. What else? Maybe we could state random matrices. when we get to it, I'll explain how random matrices are a 2D statistical physics model. And you could also add lozenge tilings. And for all of these, it's expected that chi, oh, maybe I'm a bit too high here. I'm going to ask to write lower. We expect that chi is related to another exponent. The transversal fluctuation exponent. So what is that? We're looking at the passage time between the origin, say 0, 0, and n(E1), so n0. We can draw a straight line between the origin and n0, and look at what the geodesic between those points looks like. Okay, and then we can consider the segment between 0, 0 and n0, and look at the maximum, say it's over here, the maximum displacement of the geodesic from that segment. Okay. Intuitively, the transversal fluctuation exponent, C, describes the magnitude of that maximum displacement. So I'll write down some possible precise definitions of n to the C, but part of the problem in this business is finding good definitions that are strong enough to prove things, but not so strong that you can't say anything about them. But intuitively, C is such that the geodesic between 0, 0 and n0 is contained with very high probability in a cylinder of width n to the c about the axis, about the straight line between 0, 0 and n0. Okay, so what are possible definitions of C to make it more precise? Yeah, of course, but of course, we're interested only in the growth rate. So when I define the exponent, you'll see that really what matters is the growth rate. So if you wanted the probability to be really close to 1, you would have to make this constant large. So, for example, if we define, say, gamma 0 and E1 to be geodesic between 0, 0 and n0. And for this discussion, I'm going to assume that it exists and is unique, geodesic between these 2 points. Then what we want from C is that the limit as n goes to infinity of the probability that the geodesic between 0 and NE1 is contained in the cylinder centered around this axis and of width n to the c plus epsilon. We want this probability to go to 1 for every epsilon positive. So if I expand the cylinder a little bit by some power, then with very high probability, the geodesic is contained in this cylinder. So C here is, maybe let me write it over here. So C plus C n to the alpha will be the set of X in say RD, such that the distance between X and the segment from 0 to maybe 0 and E1 is less than n to the alpha. Okay, we have a cylinder like this around this segment. And if we expand the cylinder a little bit, then with very high probability, the geodesic will be contained in it. But we don't want C to be lossy, so we also want that if we shrink the cylinder a little bit, the geodesic is no longer contained. So one way that you could achieve this is by taking the infimum over possible exponents, such that this condition here is satisfied, so that the limit, for example, maybe this limit doesn't exist, but that the limit of over here is positive. So you could define, one possible definition of Xi would be as the infimum over exponents alpha, such that the limit of this probability that gamma 0 and E1 is contained in C n to the alpha, that this one is positive. Okay, so you increase alpha until, with a decent probability, the cylinder is contained in. Okay, so what's expected, and why did I introduce this, even though I want to focus on the fluctuations of the passage time itself? Well, that's because before we get started, it's a good idea to understand what is probably true. Okay, and what is probably true in this case, so not just for first passage, but for all these models, and is very partially proved in some special cases, is that there's a relation between these two exponents. We started over here saying that for all these models, we expect a relation between chi and this exponent C. So what is that relation? We expect that we have two relations between these exponents, just algebraic relations. Chi is equal to linear relations, in fact. Chi is equal to 2xi minus 1, and also chi is equal to c over 2. So these are two linear relations, and they're linearly independent. So in fact, they allow us to solve for chi and xi, and they give us these exponents 1/3 and 2/3. But this is actually a better way to write the relation than actually solving for their values, because as I said, in most cases, we have no idea really how to prove these relations. And so the best we can do is approximations. And of course, it's easier to approximate these than to meaningfully approximate these numbers 1/3, 2/3, because we're so far from actually getting there. Okay. Yep. Oh yeah, so this will take a while because random matrices is not obviously a 2D model, but I just want to answer your question very quickly, but I'll come back to that. So how do you get a 2D model from random matrices? If you look at, say, the Wigner matrix, so if this doesn't make sense to other people, I'll come back to this and explain it. If you look at the random matrices, the obvious analog, and in the case of LPP, actually, there's an identity and distribution of the passage time, would be the top eigenvalue. Let's call it λ1. And the top eigenvalue will fluctuate in a certain scale. We know that the top eigenvalue will be, say in the Wigner case, it'll be at 2, the edge of the semicircle, plus some order n to the minus 2 chi. So this is, it depends on how you scale you scale your matrices. I usually scale it like this. Okay, so the chi exponent is this. It's contained in here. So this is the chi. This is chi minus 1, right? But what is the? You ask what is the xi exponent? So here it doesn't look two-dimensional. To see two dimensions, what you should do is instead of looking at a single eigenvalue or a single matrix, you should embed this into a continuum of matrices, into a process of matrices called Dyson-Brownian motion. If you look at Dyson-Brownian motion, then you start getting something that looks more 2D, right? And then this top eigenvalue is not just one point, but it's actually a curve around this expanding semicircle. And then this xi exponent is a correlation exponent in this time direction. Okay, so it tells you how much you have to go laterally before things decorrelate. I'll get back to this. Does it make sense? Okay, so this is the expectation, but so this just like the value, just like this statement, apparently much weaker statement that the variance just grows polynomially with some order n to the 2 chi. It's not proved for FPP models, with the exception of one model that's due to Sepelainen, but that's actually a bit different from the things that we accept as FPP in this class, in these courses. So not proved for FPP, and known, as we will see, in course number 4, as you will see, known for some very specific LPP models and also polymers. Okay, so both the exact value and these, sort of geometric proofs of these scaling relations are known in both of these cases. So meaning for LPP and some polymer models. Okay, so when I say expect, where do these numbers come from? So who expects this? There are simulations, but I think the papers or the people who are always mentioned in connection with these exponents are first Kardar, Parigi, and Zhang. They worked in the 80s, not really on first passage or last passage. They were interested in more general growth models that they described using a continuum theory, the KPZ equation, but they also guessed these exponents. And then getting closer to last passage or first passage percolation, but still very much on the physics side of things, we have work of Krug and Spohn. And if you're interested in reading a bit about this, I guess from 87 and 88, I would mention 2 papers. First, 2 sources. First, there's a book called Kinetic Roughening for growth models, for random growth models, for growing surfaces. I think this book is quite difficult to read for mathematicians, but if you look at the beginning, the first 20 pages, you may get a sense of how this connects to last passage and these predictions. And there's also, in my opinion, somewhat easier to read for mathematicians. It's a paper called Universality Classes for Random Growth Models for deterministic surface growth. Even though they mentioned deterministic in the title, they actually mention how the Eden model, they give some intuition, some heuristics for how the Eden model that was mentioned by Jack, or maybe Michael. So this random growth model that's basically equivalent to last passage percolation with exponential weights. They explain how the KPZ equation supposedly relates to that growth model. Okay, so that's where these predictions come from. So they come from simulations and some physics arguments. But as far as I understand, even physicists agree that there's not a fully robust mechanism that has been, a geometric mechanism that has been identified that leads to these exponents. But we have some guesses that are good heuristics for why we would expect these exponents, and I wanted to present these arguments to you. Okay, any questions? So let's look at some, let's stay in the realm of physics or dreams, and let's look at some arguments in the context of FPP, so first passage percolation, for why you would expect these relations, or why you would expect these 2 types of fluctuations, the fluctuations in the passage time itself and the much more geometric fluctuations of the geodesics about straight lines to be related at all. And again, this is very far from being proved in a satisfactory way with satisfactory definitions of the exponents. But if we make a lot of assumptions, we can get an argument that looks reasonable. This is heuristics for the scaling relations. And when I say scaling relations, I mean these 2 relations here. Okay, so first, let's give a very common heuristic that's appeared in many forms in the last passage and first passage literature for a comparison between chi and 2c minus 1. And there are rigorous versions of this argument that have been developed. The big assumption here that is not something that we know how to prove, not by far, is we're going to make a strong convexity assumption on the limit shapes. That maybe we're going to say that when we look at the mu, at the time constant as a function of the direction, we're going to ask that this be twice differentiable and strictly positive. And so this is very, very far from anything that we can prove. But okay, let's accept it. It seems to be generally accepted that this is true for reasonable distributions. Remember, mu here was this time constant that we obtained from the subadditive ergodic theorem. It's the deterministic approximation of the passage time on large scales. So the idea to relate chi to 2xc is to say that mu tells us, mu and the exponents chi tell us how far the geodesic from 0 to NE1, say above the point n over 2, 0, how far it can stray from this horizontal axis. So we know that reasonably we can expect the height of the intersection of that geodesic with this vertical line here to be n to the c. Okay, that's the definition of n to the c. And then we look at the geodesic between these 2 points, and let's approximate it in 2 different ways using the time constant. On the one hand, t0 and e1, we can write it in terms of this time constant and the exponent chi as n times mu e1. That's the first order approximation. And then the fluctuation exponent tells us that the error is of size n to the chi, right? Now, what did I do here? I replaced t by this, by the time constant. This is already using an assumption about the fact that the non-random fluctuations and the random fluctuations match. But we're in space here anyway, so let's just keep going. This is believable. If the quantities make sense, then this equation would make sense. The problem is that we don't really know that these quantities make sense. Okay, so we know that we can find a point between, on this line here at height about n to the c, such that actually the passage time is realized going through this point. So let's split up this, let's call this intersection here n to the c e2, since this is the states at height n to the c e2. So let's split up this passage time here into 2 pieces. First, the passage time from 0 to this midpoint, to the intersection with the midpoint. And then, so this is n e over 2 e1 plus n to the c e2, plus the remaining part, starting at n over 2 e1 plus n to the c e2, going all the way to n e1, okay? So we have this additivity across the geodesic that supposedly intersects this, this straight line, okay? So now let's separately expand these 2 quantities using the same approximation that we used here. What does this look like? Okay, so let's start with T0 n over 2 E1. Let's factor out an n over 2, so we're left with 2 n to the c minus 1 to match this n here, times E2. And now we can expand using, okay, we can, intuitively, we should be able to expand this as n over 2 times mu in the direction E1 plus 2 to the n c minus 1 E2. Of course, here we're using the subadditive ergodic theorem, or the existence of this time constant at a random point, but okay. And the fluctuation should still be of order n to the chi. Okay? And let's apply the same expansion to this here, starting from just, so we want to expand this, we have n over 2 E1 plus n to the c E2 and E1. Okay, and this one, if we want to put it in the same form that we have over here, we can just use the inequality in distribution and shift this, say that this is equal to the passage time from 0 to, so this is n E1, so we're left with n over 2 E1 minus n to the c E2. And now this looks exactly like this guy, except that the plus has become a minus. And so we can expand this as n over 2 mu e1 minus 2 n to the c minus 1 plus order n to the chi. Okay? So this is heuristic, but now it's clear what the next step should be. We have mu, this supposedly twice differentiable function, add a number plus a small number. The same thing, add a number minus a small number. So when we add them up, when we Taylor expand and add them up, we're going to get a second derivative, right? And the second derivative will have in front of it this e2 times n to this power squared times n. Okay, so let's expand. So maybe let's give these guys a name. So this is star and triple star. So adding star, double star, sorry, and triple star. Sorry, I'm writing a bit too high. Adding these, we get the first order is n mu e1, and that's lucky because that's what we get over here. But then the next order comes from a first order Taylor expansion of this, but this and this guy are going to cancel, right? So, sorry, I guess over here, I have to write it like this. Okay, so we're only left with the second derivative. And what are we left with? The second derivative looks like n to the 2c minus 1. So it's 2c minus 1 squared from the second order expansion, multiplying this n, right? We're adding 2 plus 2, which is 4, and dividing by 2, so we're left with 2, and there's a 1/2 from the Taylor expansion, right? Okay, and then we're left with the second derivative of mu, sorry, at e1, and this is in this direction e2, but we made the assumption that this term is positive, n plus an order n to the chi. Okay, but we made this assumption that this coefficient is going to be positive, the coefficient in front of n to the 2c minus 1, right? But now we're comparing this, which was one possible expression for t0 and e1, to this expression. The first order terms n mu e1 and n mu e1 match, okay? But if this term is going to be absorbed by n to the chi, by the error, it has to be that the n to the chi term is bigger than this, right? Otherwise, there'd be a discrepancy. If this is too small compared to this, here we have a large term, small is equal to small, that doesn't work. So it must be that this error can be absorbed into n to the chi. In other words, n to the chi has to be bigger than n to the 2c minus 1, and that's this relation. Okay, this is actually a fairly convincing argument, but the gigantic problem here is that it relies, there's other, problems of how you would set it up exactly to make everything work, but the main problem here is this assumption on the curvature. It's very, sorry. Oh yeah, so I'll actually mention, so, yeah, okay, very, very good. So you'll see a version of this, because there are rigorous implementations of this for certain definitions of the exponents. So let me state for you some, or give you some references for versions of this argument. And what do I mean by versions of this argument? It's the general idea of trying to bound the fluctuation, getting a bound for the fluctuations, or understanding the fluctuations by looking at two different passage times and comparing the difference, looking at their difference, or comparing these two passage times geometrically. This comes up in LPP with these stationary models where we have a parameter that allows us to change the direction, and if we change the direction just enough so that we match this n to the c difference, then we see the exponent for chi appear, and there's also an argument due to Auffinger and Damron that gave a simplified proof of a rigorous version of this first scaling relation. Yep. Well, I guess He said we need this to be strictly positive, right? So if you don't know that it's strictly positive, then this term is not there. It's non-negative, right? Because we know that it's convex in FPP, and LPP would be non-positive. But if it can be zero, then you don't get a contradiction. You get n to the chi is equal to n to the chi. Yeah, well, that's another thing. It doesn't need to exist. But if you were actually on a flat region, then you wouldn't get any. It wouldn't tell you anything about Xi. Okay, so as I said, this argument is tantalizing because it makes a lot of sense. And indeed, versions, so a form of the scaling relation chi is equal to 2xi minus 1 was proved by Chatterjee, Chatterjee in 2008, and a simplified proof, a simplified version of the argument, a simplified argument rather, with weaker assumptions. In particular, Chatterjee used a strange assumption on the edge distribution that was called nearly gamma, that has since disappeared from the literature, thanks to work of Michael and Jack. And myself. And the simplified argument was given by Auffinger and Damron in 2011. Maybe the paper appeared in 2012. Okay, so what's the catch? When I did this argument over here, I wasn't very careful about what do we mean exactly by chi and xi. But when you actually want to implement this, any sort of argument, you actually have to start, defining what chi and 2xi minus 1 mean. And just saying that t behaves like deterministic plus n to the chi doesn't cut it. You have to actually give a precise definition. And the problem with both Chatterjee's argument and the simplified version is that the versions of chi and xi that it requires are very strong. They require basically exponential concentration of the corresponding quantities on the correct scale. Okay, so this is using versions of chi and xi requiring exponential concentration. But since Michael will be talking about this, I'll leave it at this. All right, so this is one of these possible scaling relations and a geometric argument for why it should hold. Again, in first passage percolation, we don't really know how to make this work for reasonable definitions because we don't even really know that the exponents exist for reasonable definitions. But the next thing I want to show you is a heuristic for the other scaling relation that I stated, which was chi is equal to xi over 2. And this will also require very strong assumptions that, except for exponential FPP, we don't really know how to even approach. So this is the complementary scaling relation. And instead of convexity, here the assumption will be actually a bunch of assumptions about Busemann functions, the object that Michael introduced, and that sorry, I don't know your name. Yeah, that Daniel had a question about Busemann functions not along geodesics, but along a certain direction. And here we're going to assume that Busemann functions in a certain direction not only exist, but also have very good properties. So we're going to define first the Busemann function. In a direction, I guess we'll always work with a fixed direction, so let's just call it E, and associate it to X and Y. And remember what this meant. It meant that we look at X and Y, we pick a direction, so this is the direction E, and then we look at the geodesic in that direction, whatever that means. And we calculate the passage time, the difference in passage times rather, between T, X, and E, and we subtract from this y and e. So this picture already contains an assumption that ultimately these two, the geodesics emanating from x and y will coalesce. And so that this computation here, which looks like an infinite computation, is actually going to be just a difference of finite passage times between x and this point here and y and this merging point. Okay, so that's already an assumption, but we'll need even more assumptions. So the next assumption, so we will assume that this exists. We assume the Boltzmann function exists in a direction. And if you are confused about why I'm saying we assume that it exists, given that Michael gave a proof of the existence, the difference here is exactly the thing that was discussed this morning. We're not choosing a given geodesic here. We're choosing just the direction. So we're assuming basically if we wanted to use the monotonicity argument that was given for the existence, we would need to know that there's actually a geodesic in that direction, and that we could use that to actually define this Boltzmann function. But now again, we're in space here, so we just assume that things exist, and since we're already making this strong assumption, let's add even more assumptions. We're also going to assume that we have a certain expansion for the Boltzmann function. So what should the Boltzmann function look like to first order? So we're going to add a second, so this is assumptions. So the first assumption maybe let's call it A. We want this to exist. The second assumption, B, is we want the Boltzmann function, say, in the direction E from 0 to x, to have the following expansion. We have the gradient of the time constant dotted with x plus order of x to the 1/2. Okay, so this is called diffusive behavior. First of all, why does this make sense? So first, why would it make sense that the first order is given by the gradient of the time constant, and why would it make sense that the error term would be x to the 1/2? Well, the first thing to understand this term, that's fairly easy. We can just look at the definition of the Boltzmann function. We have x and e, which in distribution, we can shift this and say this is the same as n e minus x, right? And if we do the same thing to y, and e minus 1, and then we expand this one, so we expand this passage time using the time constant. What do we get? We get n times mu at e with an error, x over n, and here we get n times mu at e with an error, y over n, right? And now we're looking at the difference between these two quantities, right? We're looking at the difference between this guy and this guy. Since we want to analyze the difference at e plus a small shift, we should expand, right? We should look at the derivative. So that's what is going to give us the gradient here, and the dot x is just the difference between x and y. Okay, so let me write this. So if we assume that mu is as nice as we want, so if we assume that it is actually differentiable, then these Taylor expansions, or these expansions, should tell us that e, y, and e. Of course, I wrote it like this here to make it clear, what the next step would be, but we can also do the Taylor expansion at this level, do the supposed expansion at this level, and then use the translation, try to translate in gradient of mu. But let's forget about all this. We're just telling stories here. If we expand this, the first order should be the difference between these two should be the gradient of mu at e times x minus y. Okay? This is from a Taylor expansion. Now, what about this guy? Why would the error about this first order term be of order x to the 1/2? Okay, so I think Michael mentioned the additivity of Boltzmann functions. Did you? Okay, so remember the Boltzmann functions, suppose we're interested in the Boltzmann function associated to x and y. We can build up this Boltzmann function by looking at a path from x to y, looking at the edges on this path, and the associated Boltzmann functions. So let's call this path here, say that x is equal to x0, and then there's an x1 and an x2, continuing to xn equal to y. And I can write the path from x to y, you can write x minus y as successive differences between these. So x0 minus x1 plus x1 minus x2, and so on, plus xn minus 1. And I can consider the Boltzmann functions associated to each of these increments, each of these individual edges, right? And the Boltzmann function be0x, I can write it as a Boltzmann function of order, let's call this m. So I shouldn't have called this little n. Let's call this little m, lowercase m here. I equal 1 to m of the Boltzmann function be associated to x I and xi plus 1. So this is a minus 1. Okay. So maybe we should start at 0 here. Okay, so we've written, and here m is of the order of the distance between x and y, right? So that's the, we can find a path of order x minus y, steps, and we can decompose this Boltzmann function linearly into Boltzmann functions across these individual steps. And then this assumption here, okay, if we assume that each of these guys has an expansion of this type, then this first order term will just come from summing up the first order terms over here, right? If I expand this, it's equal to this, and on this side, each of these will give me a gradient of mu e times xi minus xi plus 1. And now this error term, and also this word here, diffusive, suggests that what's happening is that the correction to that first order term are more or less independent or weakly correlated. Okay, so why would we expect, this is an assumption, we don't know how to prove this. In some LPP models you can prove this, but why would we expect this? Okay, what's a possible guess? Well, how can you think of this Boltzmann function here, xi plus 1? One way to think of the Boltzmann functions is to think about, a point very far away, and to think about passage times from this, look at things backwards. Think about this point very far away, and from this very large distance, what is the difference between going to x and going to x1, x0 and x1? What is the difference in passage time? Okay, the difference in passage time, as Michael explained to us, is going to be bounded by the passage time of this individual edge. Okay, and these individual edges are independent. If you look from a large distance, it's conceivable that the difference between the passage time over here and the passage time from this large distance to here, that these are independent across different edges. Okay, so this is not proved, but that's the expectation. If we accept this guess, then this square root correction here just comes from the number of terms in this sum. Okay, so now let's assume these two facts, or assume these two guesses, and try to derive this relation chi is equal to xi over 2. Sorry? Yeah, so the model of last passage percolation that I think hasn't been defined yet is very analogous to first passage percolation. And for some choice of some choice of weights, the model is not only exactly solvable, but it has a certain, there's a stationary version that allows for many probabilistic arguments that don't require solving everything. And a lot of these arguments that I showed here, actually, it's possible to implement them and to show, for example, existence of these Boltzmann functions and study their behavior in much more detail than is known for. But Martin will talk about this in course number 4.
Now, it looks to me like that n is approximately x minus y, and that's the way that should be order of x minus y to the 1/2. Why is it x?
Oh, so here I'm looking at the Boltzmann function between 0 and x. I shouldn't have done this. I just switched. Okay, so let's make a third assumption. Okay, I said we're going to make a third assumption, and this is this assumption of not only coalescence, but coalescence bound in the coalescence time. So we're going to start with x and y at distance n to the c from each other. So we're going to look at, say, 0. And so now, from now on, y is equal to, so maybe x is equal to 0, 0. Y is equal to n e2. So this is 0, n. And we look at the Boltzmann function in the direction e1. And we're going to assume that, so this is n to the c, sorry. So the distance between them is n to the c. And one feature of n to the c is that when 2 points are at distance n to the c, by looking backwards and thinking about how much geodesics can spread, 2 points that are at distance n to the c from each other, if you look in a fixed direction away from these points, the geodesic between these points, the geodesics emanating from these points in that direction will merge within a tight region. So the distance here will be something like z, where z is some fixed number times n. Okay? And what that means is that when we look at the Boltzmann function in the direction e1 associated to 0, so that's x and y being n e2, n to the c e2, it means that we can represent this no longer as a limit, but just as a difference of this passage time and this passage time, okay? So we can write this exactly as t0 z and e1. That's the distance between the passage time from 0 to zn minus t n to the c e2 z and e1. Okay, so now we have all the steps, and once we've made so many assumptions that nothing can go wrong anymore, what we're going to do now is just expand this Boltzmann function in 2 different ways. Okay, just like we expanded the passage time in 2 different ways before. So one way is using this expansion. And so using this expansion directly, we would find gradient of mu in the direction e1 times n to the c dotted with n to the c e2 plus our error, which is going to take this distance n to the c and square root it. Okay? So this, so we had 3 stars already, so let me call this 4. So this is the expansion 4 applied to this guy. Now, these guys, these 2 passage times, we can also expand them using the time constant. So to first order, this guy here is n times mu e1 times n times z e1 plus order n to the chi. And this is getting a bit too small. What can I do here? Let me put on order n to the chi that will be common to both of them at the bottom here. And I can also expand this guy. And if I expand this guy, I get n times mu of z e1 minus, from this guy, I get n to the c minus 1 e2. Okay? So because this is a bit cluttered, let's take this side and match them on the other at the board over here. So by expanding the Boltzmann function in the direction e1, or the Boltzmann function e1 0 n to the c e2 in 2 ways. On the one hand, I had over here the gradient of mu e1 dotted with n to the c e2 plus order n to the c over 2. And then on the other hand, I had this difference here. But what am I going to do with this difference here? Of course, I'm going to Taylor expand. I'm going to get the gradient of mu dotted with this number here, right? This is a Taylor expansion of this to first order. We're just looking at the derivative. So I'm going to get gradient of mu times, so there should no longer be an n here. No, there should be, sorry, should be an n. And I'm going to get the gradient of mu at z e1 times n to the c minus 1 e2. So I get gradient of mu at z e1 times n to the c e2 plus my error is n to the chi. Okay? Now, because z is just a fixed number, it's independent of n supposedly, or it's tight, let's say, I can just use translation invariance to get rid of this z and match these first order terms. Okay? And that means that n to the c over 2, so this error term should match this error term. So if they're both positive, they must be of the same order. Okay, and that's the scaling relation chi is equal to c over 2. So again, this argument is very believable. It's just a Taylor expansion. We love the, physicists love this. When you have something that works when you Taylor expand, it must be that it's actually true. It's just that you don't know how to prove it yet. Okay, so what is the status of this? There's no hope to make this work in FPP with current technology, but in LPP, basically all the ingredients are there. But in LPP, we have, as I said, we have other ways to match. There is a certain relation that will be discussed in course 4 that is basically an exact version of this chi is equal to c over 2. You can write a formula for the variance that relates it to another quantity that looks like n to the c, and that's it. You don't have to do anything further. But if you wanted to implement this argument, I think it would probably, what do you think? It would probably be possible. So let me just write what I said, and finally move to what is actually to reality, the mathematical reality. So this is convincing, or maybe I'll let you be the judge of this. I think this is convincing, but the technology does not exist to prove or even approximately prove the assumptions. So existence of Guzman functions, then the coalescence, and what was B, this differentiability and diffusive behavior. Except for stationary LPP models. Okay, so these are the reasons. We have a good, I think maybe you're convinced now that we have good reason to believe that these scaling relations actually make sense and are probably the right way eventually in the future will be the correct way to identify these scaling exponents. But for now, we have to find different ways. Any questions? How much time do we have left? Okay. All right, so I'm going to let me skip this part about random matrices and discuss. Okay, I'm going to start discussing what is actually known for first passage percolation. So all this was heuristics and expectations. What can we do for the model that we've actually been discussing so far? Meaning first passage percolations with IID weights and no special assumptions on the structure. So that's maybe number 4 or number 3 is what is known. What is known for FPP? So recall the guess, the target is to show that the variance of the passage time is of order n to the chi, for chi is equal to 1/3 in the sorry. Yeah, 2 chi, thanks. For n equal to chi equal to 1/3 in dimension d equals 2, and reality is that is much worse. What we can basically do, but I guess this will require some discussion, some detailed discussion. What we can do in general is we can prove that the variance is bounded by n divided by log n. So that would correspond to chi is equal to 1/2, so very far from reality. And then we can get, in dimension 2, we can get lower bounds of c times log n if we don't make any additional assumptions. This is for FPP with IID weights and no assumptions on mu. All right, so let's see. I'm just going to give you some references for this. So each of these upper and lower bounds has like glorious history in FPP. So first, for the lower bound, we have work of Newman and Pisa under some, for general FPP, but under some moment assumption. Okay, and there's also work of Pimentel and Perez for a special model with exponential weights. And then, so recently there's been okay, so I guess I should mention Chatterjee and Eric in when 20 okay, so 2020. So they reduced the moment assumptions and gave a nice general argument for lower bounds and fluctuations in similar models. And then there's also some work of Michael with Christian Houdray and Jack and Shu. Yeah, I don't know this person, so yeah. Okay, they also reduce some moment assumptions. I don't remember exactly what the relation between these two works are, but both reduce moment assumptions. Okay, and then there's very recent work which of Damron-Houdray and sorry, I don't remember. Who's the third person? The lower bound with curvature assumption, like the n to the 1/8. Yeah. Okay. Okay. So. Great. Here, so this is on the torus. So the original argument here that was given for this actually doesn't immediately work on the torus, so that requires some extra work. And then in this paper, I think also under curvature assumption, they get a polynomial lower bound. Okay. There is actually a first passage percolation model for which you can prove the n to the 2 chi exponent, but it's not of this form. It was invented by Seppäläinen in the 90s, and Johansson was able to solve it exactly. So this was for the lower bound, and for the upper bound, which is what I'll start discussing next time, we have a very important work of Beniamini. So first in Keston in the 80s. So in the 80s, proved that the variance is bounded by n. Okay, especially when he started, this is not obvious, so that chi is bounded by 1/2, and gave a constant lower bound for the variance. Then Talleyrand, one of the examples in his famous paper on that contains Talleyrand's inequality is through first passage percolation, and he gives exponential concentration. or even Gaussian concentration for T0 and E1 on scale n. And the first bound that beat just this n bound of Keston's was due to Beniamini, Pillai, and Schramm published in 2004, where they get that the variance is bounded by a constant times n over log n for FPP with Bernoulli weights, so with two weights. So not necessarily Bernoulli, but random variables that are supported on two positive values. So not Bernoulli. And after that, there was some work extending this of Benaim and Rossignol to a special class of distributions that they defined called the nearly gamma distributions. So this extends this BKS to nearly gamma. And then with Michael and Jack, we extended this to basically, most reasonable distributions under a moment assumption that was T E squared log plus E is finite. Okay, so, and we also have a corresponding upper tail bound, so we can prove that the probability that the passage time minus T0 and E1 is bigger than lambda square root n times log n. This probability is e to the minus c times lambda if you have exponential moments for some positive alpha. So I guess I'm out of time now. So what I'm going to do in the rest of these lectures is give you some ideas of how to prove these results. Okay, thanks for listening.